Good day, everyone. This is Engineer Magkuya, and we're going to have our continuation of discussion about vector spaces. For this week, we will be discussing basis and dimension. The objectives for this lecture would be to recognize bases in the vector spaces r raised to n, p sub n, and m of m comma n, and find the dimension of the vector space. Basis for a vector space. A set of vectors S composed of the vectors v1, v2 up to v sub n in a vector space V is a basis for V when the conditions below are true. So it must be a spanning set. S must be a spanning set of V, and the vectors in S are linearly independent. Moreover, if a vector space V has a basis with a finite number of vectors, then V is finite dimensional. Otherwise, V is infinite dimensional. The vector space V equal to the set that contains the zero vector consisting of zero vector alone is finite dimensional. Example, for the standard basis of R cube, show that the set below is a basis for R cube. S is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. In an earlier example, we showed that S spans R cube. Furthermore, S is linearly independent because the vector equation C1 times 1, 0, 0 plus C2 times 0, 1, 0 plus C3 times 0, 0, 1 is equal to 0, 0, 0. Has the only trivial solution. So you may wish to verify that this would give us C1 equal to 0, C2 equal to 0, and C3 equal to 0. The manual solution for this one would be provided in a file in your Blackboard section. So S is a basis for R cube. So you have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Uniqueness of basis representation. If S equal to V1, V2 up to Vn is a basis for the vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in S. Let U be equal to U1, U2, U3 be any vector in R cube. Show that the equation U equal to C1V1 plus C2V2 plus C3V3 has a unique solution for the basis S equal to V1, V2, V3, which is equal to 1, 2, 3, 0, 1, 2, negative 2, 0, 1. So to solve this problem, what we're going to do is to write the vector X as a linear combination C1V1 plus C2V2 plus C3V3. So you have C1 multiplied to the first vector plus C2 multiplied to the second vector plus C3 multiplied to the third vector. So that would be C1 minus 2C3, 2C1 plus C2 plus 0C3, 3C1 plus 2C2 plus C3. So this would form your augmented matrix A, and then the unknown vector X equal to U. We can solve this using Gaussian elimination or Gauss-Jordan elimination. So the matrix A is invertible, so you know that the system has a unique solution. C is equal to inverse of A times U. So you can verify this by finding the inverse of A such that C1, C2, C3 is equal to negative U1 plus 4U2 minus 2U3 2u1 minus 7u2 plus 4u3 and negative u1 plus 2u2 minus u3. For example, if u is equal to 1, 0, 0, this can be represented uniquely as negative v1 plus 2v2 minus v3. Basis for a vector space. Basis and linear dependence. If S is composed of the vectors v1, v2 up to v sub n, this is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. So again, if you have n vectors and the set contains more than n vectors, so if the number of vectors is higher than n, then automatically you can say that they are linearly dependent. You need n vectors to represent, you need at most n vectors to represent linear independence. So if there would be more than n vectors, automatically one of the vector is a linear vector of the other. One vector is a linear combination of the other vector. So that means it is linearly dependent. So these are some of the examples about that. R cube has a basis consisting of 3 vectors. So since this is R cube, we are expecting 3 vectors. First, second, and third vector. So these 3 vectors is sufficient to determine linear independent vectors. But since there are 4, so that means one of this can be written as a multiple or a linear combination of the other vectors. Another one, P3 has a basis containing 4 vectors. So P3, so that means you have a plus bx plus cx squared plus dx cubed. So this is P sub 3, a polynomial of degree 3. How many components does this vector have? A, B, C, and D. So that's 4 components. So that means it needs at most 4 vectors. But for this example, we have 1, 2, 3, 4, 5. So there are 5 vectors. So automatically, this set of vectors are linearly dependent vectors. Number of vectors in a basis. If a vector space V has one basis with n vectors, then every basis for V has n vectors. Again, if a vector space V has one basis with n vectors, then automatically we can say that every basis of V has n vectors. So explain why each statement is true. The set S1 is composed of 3, 2, 1, 7, negative 1, 4 is not a basis for R cube. So if it is R cube, we need 3 vectors. There are only 2 vectors, so meaning we are lacking one more vector to form the spanning, we need one more vector to form the spanning set of R cube. While for the second one, so the set S is not a basis for P3. So P3 means 4 components. So you have 1, 2, 3, 4, 5. So you have 5 vectors. So this is not linearly independent. So therefore, not a basis. For this one, for it to be a spanning set, you must have 3 vectors. So it's not a basis for R cube. So the standard basis for R cube is S equal to 100, 010, and 001. Thus, there are three vectors in the basis for R cube. So all vectors of the standard basis of R cube has three vectors. So if we are referring to any R cubes, there must be three vectors in its basis. But since the example has two vectors, so it's not a basis. While for this one, a standard basis P sub 3 has four vectors. So there are five polynomial vectors given. So that is not a basis for P sub 3.